Welcome to the pre-recording of the first half of Lecture 8 of Computer Algorithms in the 8-week summer session. This lecture is scheduled for the end of the third week. Today we are starting divide and conquer, a very important technique to design algorithms. So we will, in the first half, focus on a variation of merge sort, a well-known technique to sort numbers in time that is quasi-linear, very efficient. So what's the idea of divide and conquer? When we have to solve a problem on some input, we break the input in several smaller parts. Smaller problems can be solved better and more efficiently. So when we have solved the solutions, when we have the solutions of the smaller parts, we combine the solutions into the overall solution. So that is the general idea for the technique of divide and conquer. Let's now see how this applies to merge sort. We have to sort a sequence of numbers, so we split the sequence of numbers we have to sort in about 2 equal halves. We sort the halves, and then we merge the sorted halves. We can show in a rather straightforward manner that for an input of n numbers, merge sort runs in a time of n log n. That is substantially faster than algorithms that have a worst case running time that is quadratic. This course follows data structures, which is typically more hands-on, and even already in an introductory programming class, you take a very basic quadratic sort, like selecting the largest element of each of a sequence repeatedly. If you run this on, say, 100 numbers, it runs fine. A quadratic sort is fine with 100 numbers, 1000 also fine. But when it starts to get into the range of 1,000,000 numbers, certainly already for older computers, but even for modern computers, 1,000,000 and go up to 1,000,000,000, your quadratic sort will be very, very slow. Okay, so we live in the age of very large data sets, so efficient algorithms matter even in the time of very efficient computers. So with divide and conquer, we can often go to n log n or to sub-quadratic time. Sub-quadratic time is that you have n to some power where that power is between 1 and 2. We will illustrate this with the algorithm of Karatsuba on integer multiplication in the next pre-recording or still at the last part of this lecture. Okay, what do we consider? We actually consider merge sort, but you have covered this algorithm already extensively in data structure, so it's a variation of merge sort. If you do not know what is merge sort, have forgotten it, then no problem. Our presentation is self-contained. So we will count inversions. So what is an inversion? So in any sequence, if you count the number of elements that are smaller than the current elements. So you want to sort a sequence in increasing order. It's obviously not ordered if the largest number comes first, as is here in this example. So the first number has 7 inversions. 8 is obviously larger than all the other ones. So if you count the inversions, then you kind of measure the disorder in a sequence. How many swaps should you do to rectify the sequence? So the higher the number of inversions, the more disorder there is. So you can go through this list one after the other. So we take the number 8, we count 7 inversions, then for 5, 5 is larger than 2, larger than 4, not larger than 6, but still larger than 1 and larger than 3. So for 5 there are 4 inversions. 2 there's only 1 because 1 is out of place if you like. 1 has of course no inversions, but 4 has 2 inversions and 6 has 2. So we ran through the sequence of numbers one after the time, and if you count now, 7 plus 4 plus 1, so we are already at 12. Count two more, we have 16 inversions. To make this presentation a little bit appealing, you could also consider this as a geometric problem. So for the sequence of 8 numbers, we have the 8 numbers at the right column, so the red dots, and then the green dots are the indices for their position. So the indices that, and then we can see if you start to count, and we will do the count, that there are as many inversions as there are crossing line segments. So the problem that we will solve can be solved in a straightforward manner by going through all the elements essentially twice. So this is the quadratic sort. We can do better by divide and conquer. So we count the number of inversions in 2 halves. And then we add up to these counts the inversions between the 2 halves. So here is a very simple instance. So we have the sequence 4, 3, 1, 2. And actually you can see that there are 5 crossings, but you can do this geometric count a little bit more in a more organized fashion by saying that there is one inversion, 4 comes before 3 in the first half. There's no inversion in the second half. 1, 2 are perfectly ordered. So there's 1 when you look at the 2 halves. And then if you look at the crossings between the 2 halves, you see that there are 4. So in total we have 5 line crossings. We have 5 inversions in this sequence. Now for the running examples are very small, so it looks, if we are introducing divide and conquer, that it's much more complicated. And indeed, if you have small sequences, simpler algorithms do usually better. That's fine to choose a simpler algorithm. Here is the algorithm demonstrated on the larger running example. So we have at the left 16 inversions. We look then at the 2 halves of 2 sequences, and you can already see the second sequence is you have 3 inversions there, but we go to the base case. So dividing in 2 has the advantage that the number of times you have to do this is logarithmic in the total number. So this is where this 2 log comes in also. And this has the advantage of rapidly going to the base case. So the base case is 2, where we have 2 inversions. Okay, there is dividing in two, counting the halves, but then there is the merging. So how do we do the merging? Well, we have 2 on the base cases, and then we have 1 in the bottom and 4 in the top. So this is when we come back from the base case, from the 4 base cases. Actually, we had 8 numbers. Um, So if you I should actually say that the base case is 1. So the middle sequence is something that there is no inversion there. That is in the algorithm the base case. But it's trivial there. We add to 0 either 1 if there is an inversion. So this is for the top one. We add 0 for the second base case, 1 for the third base case, and 0 again for the last base case. So we have 4 base cases. They contribute 2 in the count. Okay, so when we then count between the first 2 base cases, we see 4 crossings. In the second base case, there's only 1. Okay, so let's continue. Now we are in the next, coming back from the recursion. We have counted how many inversions there are in the halves, both halves, total 7. Now we need to add we need to count the inversions in between the halves. And how many do we count? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in total we found 16. So that's what we computed with our basic quadratic running time algorithm. Okay, so that's the problem. The first exercise is inviting you to formulate in words your understanding of the problem, by showing that the measuring of the disorder by counting inversions is equivalent to counting the line sequence. And showing means that you can write an argument for a formal proof. We run divide and conquer by recursion. Recursion is, if you like, a programming technique. In mathematics, we have the proof by induction. They're actually equivalent. It's an equivalent technique. In computer science, you talk about recursion. In mathematics, you talk about proof by induction. So this is a mathematical computer science course. We unify both. It's just a matter of language. So if you have to show this, you build a proof by induction on the number of line segments. If you have 2 line segments, then either you have 0 or 1 crossings, either you have no inversion or you have 1 inversion. So that is the proof of the base case. And then you assume the induction hypothesis. So what does this mean? Well, if you have the number of inversions for any sequence less than any number n, if that number of inversions is equivalent to line crossings, then we have to show that it also holds for n. And you do this by the induction step is actually counting the inversions between the 2 halves, which corresponds to counting the line segments that start in the top half and that end in the bottom half. That's the solution of the exercise here. Formulate what you need to prove. What is the induction? On what will the induction happen? And then also the base case, state the induction hypothesis, what needs to be proven, and then write the proof. So this exercise looks complicated. It will become clear because this is actually the introduction to the algorithm in words. So here is the sort and count algorithm. It is sorting, so it is very similar to merge sort, except that we now have the number of inversions with it. So you could say that it's a merge sort that kind of gives a measure of the disorder. So sorting is an important problem if it turns out that the sequences that are sorted have a very low inversion count, then there are techniques that may speed up. So merge sort is a very general method. If there are only very few inversions, then you can do probably better than n log n. So this could also be used as a diagnostic for your data sets. Also deciding a little bit, do you sort once and for all, only once, or do you sort many times as soon as your data set gets updated? All right, the base case is when somebody gives you a list or a sequence of n elements. Well, if it's an empty list, then also should be 0 and the empty list returned. Otherwise, we cut the number of elements in half. If that number is odd, we have that A will contain one more element than what is in B. We have the recursive calls where we are counting the number of inversions on each half, and then we do the merge. And in the merge we also count, and we return the total count, first half, second half, the inversions between the halves, and we return that number along with the sorted list. Okay, so that is the algorithm, except that we haven't really specified how we do the merge. So this algorithm is a general pattern for divide and conquer, splitting in half. The merge is what is typically where you need to apply the technique to the specific problem at hand. Okay, let's go again very slowly through the example and see what happens when we merge the last two halves. So we have two sequences, A and B, and we will have to count. So the two sequences A and B, you see them listed here, 2, 4, 5, and 8. There is no inversion. There is no inversion 1, 3, 6, 4. So we will merge like in merge sort. So each time popping the smallest one. One is in B. So it makes an inversion with all the elements in A. So we will increment the R, the number of inversions between the two halves, by the size of 4. We can pop 2. 2 is smaller than 3, the next element in B. And then we are again at a situation where B has the smallest element. Okay, so now the size, so 3 makes an inversion with 4, 5, and 8. So we have to increase the count by 3. So this gives us the count of 7. Then we can pop 3, pop 4, and we are left, and also we can pop 5 because 5 is less than 6. So there is no inversion. So there is no inversion if the first element in A is less than the first element in B. So that is what is the first important property here. So we only have to increment the number of inversions when the first element in B is less than the first element in A. And then actually, because the list of A is sorted, then that first element in B that makes an inversion will make an inversion with all the other elements. So you see that we arrive by merging and counting each time the size of the first half, we have arrived at the correct count for the number of inversions. Okay, so this is the introduction to the algorithm. Here is the formal description of the merge. So as long as the sequences are not empty, the algorithm will compare the top element. So we have stacks, if you like, and we can look at the value of the top without popping. So if the first sequence starts with an element that is less than the first first element in the second sequence, that element will not make an inversion with the second element, and we pop it and we append it to the sorted sequence. So the appending, so I said that this lecture is self-contained. This also explains merge sort again. We are interested in the count, and you cannot have an inversion when the top of A is less than or equal than the top of B. You have inversions when the first element is less than the first element in A, and it will make an inversion with all the elements in A. So that's why we increase after the pop, we increase the number of inversions by A. So actually the very critical element, so this is the merge and merge sort, but it essentially differs only in one line from the merge of merge sort. Okay, when the sequences are empty, there are no more inversions because we have already taken the inversions of the halves into account. So there is no, in this stage we are interested in the inversions between A and B. Okay, so if this is not clear, I would invite you to go back to the previous slide, or in this pre-recording, go back to the example. So these slides could have been flipped. I introduced the algorithm with an example, but the example also illustrates this algorithm. Okay, very good. In both the example and the algorithm, I motivated the correction, the correctness. I actually motivated why we incremented when we increment. Any algorithm would actually need a proof of correctness and also actually termination. It terminates because merge sort terminates, obviously. So we state the correctness with a theorem, and the theorem is implied by the lemma. The sort and count does not count at all. It's merge and count that does it. The key observation is that it's only that we can have an inversion when the first element of the second half is less than the first element of the second half. And we use the fact that all the elements in the first half are sorted. So that's why we can get away with a very quick addition. And in some sense, the fact that this is a quicker count, you can see that we don't count like in the quadratic sort, one after one. So if the number of inversions is very high in a list of millions, you do a lot of additions if you do this in the straightforward way. Here actually you will do a relatively few additions, and that could be an extra exercise. Estimate bound the number of additions that this algorithm does. Okay, I ran ahead, so I hope that the correctness is clear. So I have not given a formal proof of the correctness, but it should be clear that the key observation can be turned into a formal proof. How would you prove it formally? You will first specify what needs to be proven. It actually says it in the lemma, but you will indicate that that single statement here suffices. So you update only once, and that happens in the if statement in the algorithm. So you in a proof that this counts as a proof, not as kind of a intuitive statement why it is true, you would formally refer back to the if statement and why this count only happens in the end. Okay, running time. So the running time will be the same running time as the running time of merge sort. And when we introduced the upper bounds, the efficient algorithms, I already gave a proof of the theorem. So we've seen this already. But this is another algorithm. And to make this lecture self-contained, it serves as a separate proof, and actually you would need a separate proof of the running time. We measure the running time on the size of the input. So the size of the input is the number of elements in the sequence. The key step here is to also realize that the merge and count is linear in the total number of elements. So the divide and conquer with 2 follows a straightforward pattern. So it's obvious that if you cut the size in half and you apply the same method to it, that the running time of the total running time is bounded by 2 times the cost of the main sort and count. The main activity actually goes into this here. So there should have been a lemma. The lemma that actually says that the merge and count is actually linear. So this is the lemma here, which is just stated as a sentence. The merge and count runs through every element of A and B, and thus only a constant number of operations per element. In particular, it does one comparison. It does the append. So each element is appended to a list, and this append happens exactly once. The comparison happens for every element. So we compare the tops. So, but um, it should be clear that as the sequence decreases by one in every step, the number of comparisons is bounded by n. The number of assignments is done at most n. So assignments to the count. So in some sense, the number of times that you increase your count might also be or have a worst case upper bound that is n log n. Okay, now the main theorem says that the sort and count, counting all inversions, runs in time n log n. So if you are therefore implementing your own merge sort, you could as well do this extra option where you count the inversions, measuring the disorder in your sequence. All right, we will, in the later part of this lecture, look at the solving of general recurrences. So the proof by induction is also referred to in discrete math by solving recurrences by substitution. The proof lists a more complete formal proof than the one that we have given earlier in the lecture. So in some sense, it's good that we go through this once more in a more formal manner. It's proving by induction, starting with the statement we do the induction on what? On the size of the sequence. And with the base case, there's really something that can go wrong because the logarithm of 1 is 0. So the algorithm has actually base case 1 or less, but if you apply the logarithm on 0, you shouldn't be doing this. On 1, you get 0, and it's awkward to say that something is bounded by order of 0. Does not make sense. So we have to argue here that counting or sorting two elements happens in constant time. So, and that is true. So we have done the base case. Then the induction hypothesis, we assume that for all sequences less than n, we have a running time bounded by k log n, where k is the size less than n. And then in some sense, we have the first midterm exam looming upon us. So what does the big O again mean? It means that there are constants, and here is now the creativity. This happens in the naming. We have constants C1 and C2 sitting in there. So in the statement of the theorem, so we cannot say that when we spell out very carefully what we need to prove, the big O notation, so we spell out in great detail what this big O notation means in the induction hypothesis, which means that there is a constant, here it's named C3, that for certain values of k sufficiently large, here I took k naught, that this T of k is bounded by the C3 times this k log k. So I'm going to use this constant here, C3. So by the way, the C2 came into the base case. So T2 is less than C2, and rather pedantically, we rewrite, we say that every constant is O of 1. So I should have pointed this out. So All right, so then here is the step where we apply the induction hypothesis. We insert the C3. The N naught is actually the same as the K naught, if you like, or the N naught is actually the upper bound for the two subsequences that you have. So you could say that the if you have this in two subsequences and one is maybe a little bit odd n, one is one higher than the other, you may have different n knots, different k knots. So this could be seen as the maximum of the two. And then we apply the properties of the logarithm, just logarithm of 2, no problem. It will be a constant. The 1 over 2 is also a constant, which cancels out the 2. And then we continue with the induction, with the rewriting, obtaining that the running time for n elements is bounded by a constant time n log n for some n sufficiently large. So this corresponds to the definition. Okay, this proof is therefore sufficiently detailed and rigorous enough that it counts to say that counting the inversions can be done in n log n time. And this is therefore our first result. Now, of course, you could argue, do the seal and floor actually matter? The fact that the list A can have one more element than the other. It will turn out not. So this is somehow in the theorem something that we have swept under the rug. You could say +1 -1 doesn't matter. But the purpose of the exercise 2 is that you consider this recurrence. So there is no constant C2 here. It's just showing that for this recurrence, you have n log n. You can use I went into great detail through the arguments in the steps of the proof. So that may have seemed tedious, but the purpose is that of this exercise is that at least you go back to this previous slide and you write things down. So you must write a reasoning similar to the proof of the previous theorem to solve this exercise. Okay, last exercise, so the end of this first part of the lecture. We counted the number of line intersections to give a geometric interpretation to our problem. Here is an other interpretation. So imagine that the numbers are kind of the centers of circles. So you consider circles where the radius of where you have one radius, and if you have no overlapping between the circles, then actually you do have an inversion. So in the modification of this problem, you could imagine that what it means to be sorted is that the circles are actually not too far apart. So, or if you have a sequence of points in the plane, you could imagine that can you kind of order them such that there is an overlap. So if the centers are larger than the radius, there might not be an overlap from between each other. Okay, so this is an alternative or an extended application to improve your geometric understanding of problems such as this. So in this first application of divide and conquer, we essentially went again through merge sort. In the next application, we will immediately start with a geometric problem that doesn't really have a relationship to directly relationship with sorting, but to which the divide and conquer principle applies. Okay, so this was an introduction to divide and conquer. I hope that this was sufficiently clear to serve as a stepping stone to more interesting and newer problems, newer than merge sort.